Hey, algebra students. You're getting lesson 18 via recorded lesson. I'm recording it. I'm not going to be in tomorrow because I'm really not feeling well, which you can probably hear in my voice and my nose. So here we are with lesson 18. So just follow along, take good notes, and jot down any questions I can answer tomorrow. First of all, you have to work on this one a little bit on your own. So think about an electronic device with a battery that you have to charge on a regular basis. What device is it? So you write yours down. I'm writing mine down. My phone. When you're using the device, how long does it take the battery to go from 100% charged until the time you plug it in again to recharge? I don't know how to answer that. I really use my phone all day. I plug it in when I'm in the car. When I go to sleep, I plug it in my bathroom, and then when I get up, it's charged. So I hope you guys have really good answers for this. I am unsure. How long does it take to charge to 100% starting from 0 or nearly 0? I'm going to say overnight. I know this isn't real, but for me, I don't pay attention. I guess I'm not the best person to take this survey. Suppose you plugged in your device when the battery was 50% charged. How long do you think it would take to recharge the device to 100% compared to the time it would take if the device was at 0%? Would it be exactly half the time, more than half the time, or less than half the time that it would take from starting from 0? I'm going to guess less than half the time. Less than. I'm sure you guys know much better. You pay better attention than I do. And I guess it depends on what type of phone you have, if it's new, if it's old, etc. So where are we going with this? Okay, not the best lesson to do while I'm at home, but we are going to work through this together. So I'm just asking you guys to dig in and try your hardest. So the next section talks about a cell phone being plugged in to be charged. The table shows the percentage of battery power at some times after it was plugged in. At what time would the battery power be 100% charged? Use the data to find out and explain or show your reasoning. So we see that our time is going up by 10 minutes. We went by 20 minutes. Again, 10 minutes. That's odd. Here we have an increase of 6, 7, 8, 9%. Here we went up by 20%. Here we went up by 8%. So what time do you think? I'm going to pause for a second. I'd love for you guys to just guess. All right, so push pause on the video so that you can work through some type of estimate. So I did some work here. Why don't we try to follow along? I wish I could get you guys up to the board and show me what you did. I looked at how much time passed, so 10 minutes, 20 minutes, 10 minutes, and how much percent increase there was. 9%, 20%, 8%. I really wanted to figure out what our change was. This is really our slope if this data were linear. So I did change in percent over change in time. I just took these values and did, I actually messed that up. I should do 15 minus 6. So hold on. This would be 15 minus 6. Divide by 10 minutes, which is fine. That's what I had in the bottom. So we have approximately, not 1.1, but 9%, 0.9% every minute. Okay, my mistake. We could also say that is 9% every 10 minutes. It's much easier than 0.9 every minute. All right, then I figured out what percentage I needed to get to 100, which was 57%. If I take that number and I use my slope, which was 0.9% per minute, I can figure out how many minutes remain. About 63 minutes, approximately. So we can say that is just over an hour. And that would be approximately 12:45. It would be fully charged. All right, what we did here is we calculated our average rate of change, which you guys know how to do. Average rate of change. And we used that down here to figure out how much time or what time it would be when we reached our full charged battery. Now to move on, so that was interesting. Took a lot of thinking that we would have talked through in class. Moving on, we can see like how long is this going to last? To try to use some data to figure out how long a cell phone is going to stay fully charged. So here we have the image shows the battery usage of a cell phone 9 hours since it was fully charged. It also shows a prediction that the battery would last about 8 more hours. Write an equation for a model that fits the data in the image and gives the percent of battery power P as a function of time since the phone was fully charged. T, show your reasoning. So P equals something to do with T. We could also say P of T. Something to do with T. So we have our input and our output. That's also going to be our input. All right. So I think personally creating a table makes much more sense. I just need some data so that I can calculate slope. So we're going to be putting things into y equals mx plus b form. So I need to be able to calculate m, which is my average rate of change. So let's do a table. Time since fully charged and percent of battery power. So this is time since fully charged. Go ahead and write that down. So time since fully charged and percentage. So we're going to start out at 100%. And then it says 9 hours ago. So 9 hours since fully charged, we're at 52%. And we're going to get all the way down to 0. 8 hours left. So 8 plus 9 is 17 hours. We get to 0. So in this table, the relationship between the quantities appears to be linear, okay? The average rate of change between beginning to end is calculatable. So if we do change in percent over change in time, we can get 0 minus 100 over 17 minus 0. 0 over 100 over 17 minus 0. So that would be a negative 100 divided by 17. I get negative 5.9 for my slope. Okay, so the battery power is losing about 5.9% per hour. My dog is snoring underneath my feet. That's hilarious. I apologize. I hope it isn't too distracting for you. All right. Well, let's look at the rate of change in the first 9 hours. Let's make sure that we have similar rates of change. So the first 9 hours, I'm going to get 52 minus 100 over 9 minus 0. That gives me a negative 5.3% per hour. Okay, we're going to actually do this one more time. I'm really curious about the other time period. So we did the whole time, we did the first part, and let's just look at the second. So 0 minus 52 over 17 minus 9. So I have a negative 52 divide by that gives me a negative 6.5% per hour. So I am interested in averaging those two. Okay, I'm curious. I think that might give us a better picture of the change totally. So for negative 5.3, negative 6.5, divide by 2. We're finding the mean or the average. And that gives me negative 5.9. Hey, that's what I got at the beginning. Per hour. Which is what I got way up here. Cool. All right. So we figured out our slope. That means that we have our equation. So P of t equals negative 5.9 t plus my y-intercept. So at time equals 0, where am I? At time equals 0, I'm at 100%. So that right there is my answer. I'm going to turn to the next slide and look at question B. Based on your function, which let me rewrite it, negative 5.9t plus 100, what percentage of power would the battery have 4 hours after this image was taken? 4 hours after the image was taken. So that would be T is 13, 4 hours after the image was taken. Let's go ahead and plug that in. My dog's too comfortable. I can't make her move. She's a 100-pound black lab and she is snoring away. She gets tired on the weekend because she doesn't get her normal nap time. Sorry, I'm talking as I'm calculating things. So I got 23.3%. That's at P of 13, so that's actually, this should have a 13 in it. If we look at it 5 hours since the image was taken, that'd be T is 14. So evaluate it at 14. You guys can probably chunk out that answer while I'm writing. So I have negative 5.9 times 14 plus 100. That gives me 17.4% of battery power. Okay, my reasoning is I came up with these awesome equations using data. Equations are based on data. It's a best fit line, so it's not perfect. But it did a pretty good job. Okay, here are two more images showing the battery usage at two later times before the battery was charged again. Okay, how well did the function you wrote predict the battery power for 4 and 5 hours since the first image was taken? So here, I think we had 23.3%. I have to go back and double check. And here we had 17.4%. I'm going to go look. And if we look here, we're at 29% for 13 hours and 7% for 14 hours. Okay, this one has to relate with that one, so it didn't do so well. And this isn't so bad. That's an okay, not an oray. So it's not terribly bad. How well did the function you wrote predict the battery power for 4 and 5 hours since the first image? My opinion is for t equals 13, pretty close. And then for t equals 14 is pretty bad. I'm not sure it was linear there at the end. So let's see what question B is. What do you notice about the change in the prediction between t equals 13 and t equals 14? Well, you can calculate at t equals 13, that was at 29%. Let me look. Yeah, 29 minus 23.3. My prediction was low by 5.7%. And then at t equals 14, my prediction, I think it was too high. I had 17.4 and they had 7. So it was over by 10.4%. To be under 1 hour and over the next is pretty shocking, in my humble opinion. So it's a drastic drop. If we added that up, it's a drastic drop of about 16.1% from 1 hour to the next. All right, last thing, and it's pretty big. So write a new equation for a function that would better fit the data shown in the last image. So we just need a little bit more information. So t times since, and then p percent. So we have 0. We're going to write down more data because we have more information now. Let's see, 100, 52, 7, and 0. We know when we're at 0. Okay, and if we do some more math, again, I'm going to do delta percent over delta time. 0 minus 7 over 14.5 minus 14 is pretty interesting. It's going to give me negative 14% per hour. Let's do 7 minus 52 over 14 minus 9. Negative 9% per hour. But then we could also do from beginning to end, okay, from here to here and there to there. So change in percent over change in time would be negative 100 over 14.5. And that's going to give me 6.9% per hour. So a new equation could be P of t equals negative 6.9 t plus 100. Okay, that might better fit because we need a steeper slope because we messed up. We didn't mess up, but our data wasn't quite accurate. At the end, it didn't decrease enough. So that's how you use data in real life. So today's lesson was sort of tough to not be there for, but we have time in our next class to talk about anything. Okay, so work hard. Good job.